Hello, everyone. So today's a glorious day. We're going to be wrapping up chapter 9. And we're going to be doing so by talking about electron excitation and trying to summarize a lot of the tricks we've learned so far this week. So we're going to start by revisiting our selection rules. And we're going to be doing this a little bit this time in terms of our new term symbols. So let's start with what our old selection rules were. And you're going to notice we're going to have a couple little twists now. So first of all, for an allowed transition, my spin can't change. So if an electron starts up, it will stay up because the photon won't change anything about my m sub s value or my electronic spin. What it will do is it will change my orbital angular momentum. So my total angular momenta, orbital angular momenta, can either stay the same or increase or decrease by 1. But again, this can only happen if if an individual orbital angular momenta changes by plus or minus 1. So if something ends up being excited but into an m sub L0 state, we may end up seeing no net or total orbital angular momenta change. But again, this can be a little bit tricky. So our final rule is now we're bringing in our total angular momenta into the conversation. So our total angular momenta can either stay the same or increase or decrease by 1, again, depending on which direction the electron went to. But it is worth noting that if I start in a state with no net angular momenta, I cannot end in a state with no net angular momenta. So if I start at 0, I have to end at 0. So this is an important thing to try and keep in mind. And again, these rules will start breaking down for heavier atoms or molecular systems. So a way to think about this is that these rules tend to apply best for systems that obey Russell-Saunders coupling, where a lot of my interaction in between spin, orbit, and total are a little bit more straightforward. So when we are applying these rules, make sure we're always considering Russell-Saunders as a backstop for what transitions are allowed. As well as you may have to, as you're going along, try and write down what the individual electron configurations will look like, as this might help you out. So let's start with a relatively straightforward case. So if I'm dealing with helium, what's going to be my ground state term symbol? So in this case, I've got a full subshell, so L, S, and J will all equal 0, which gives me one of my close friends for term symbols, the singlet S. So then we have to ask the question, what states can this atom be excited into? So I start with an L of 0. I certainly can't decrease by 1, and I can't stay the same because I'm going to go from an s orbital to a p orbital. So when I'm exciting my system, I'm going to take one of those s electrons and jump it up into a p orbital. So this will give me a final state of L equals 1, or again, a p state. And because this is an electron excitation, spin can't change. So this means I'm looking likely at a singlet p. And now I have to bring in my J rules. So J certainly can't decrease because I can't have a negative J value. And with a value of 0, it certainly can't stay the same either. So this means that my J has to go up to a value of 1. So this gives me a singlet P with a J of 1. Now, it's always worth double checking that your product state does satisfy Russell-Saunders. So I have an S of 0, a P of 1, or an L of 1. So J has to equal L, and in fact, it does. So we can extend this case for term symbols for helium in its excited state. So one electron in the 1s and one electron in the 2s. As you'll notice, I can't excite into this state directly, but I may end up relaxing down into it. So what's going to be my term symbols for this case? Well, the L's fairly easy because L of 0, L of 0, my total L will also be 0. So this gives me an S state. Now, this means I can either be in a singlet, where the two electrons are pointed against each other, or a or I can be in a triplet state where they're aligned together. And again, because L equals 0, J has to equal S. So in this case, I can have a singlet S or a triplet S state. Now, this is again where I start. What happens if I hit this specific system with a photon? Well, each one of these states may end up generating a new species. Oh, before I forget, we're going to need to still apply Hund's rules, so it's worth noting the triplet state will be slightly lower in energy. But one of our questions is going to be, what states can these two systems excite into? And not too surprisingly, each ground state will generate a different set of product states. So let's start with the simple case. Let's start with our singlet S. And if I excite this system, well, we just did this problem. My singlet S, one of those S orbitals, one of the electron in the 2s orbital has to go into a 3 or 4p orbital. And by doing so, we're going to generate a singlet p state where, again, J has to equal L. So I get a 1p1, which is exactly what we got on our last problem. So you'll start to notice that it doesn't matter what our system is, a singlet S will always generate this singlet p1 state. But that leaves us with a little bit more complicated system. I can also have a triplet S state, and it turns out this guy's a little bit lower in energy. So again, my S has to go into a P state. That's going to be mandated. So when we do this, it turns out that I can generate one of 3 triplet states. Either my my orbit ends up coupling in the opposite direction of my spin, in a different direction as my spin, or in the same direction as my spin. So this gives me 3 separate possibilities. So this is all going to depend on how this p orbital is going to couple with my spins. But if we apply Hund's rules, we'll tend to predict the triplet p with a J of 0 being the lowest in energy, though trying to apply Hund's rules to excited states can be a little messy. So our next question is going to be the trickiest of the 3. What's going to be our term symbols if I'm looking at a helium with a single s electron and a single electron in the excited p orbital? So again, due to electron excitations, I'm going to ignore any movement at the 1s orbital. It's just too low to move. And instead, focus in on where this p electron can go. But before I do that, we need to go ahead and figure out what state does this species belong to. So in this case, I know it has to be a p state because I have one p orbital and the s won't contribute. But that brings us to the question of the spins. So either my spins can end up pairing and I end up with a singlet p, and J has to equal L. Or my 3 spins, my spins as before can couple against, with, or in a different direction to my orbit. So again, this all is in agreement with Russell-Saunders coupling of J equals S plus 1, or S plus L, S minus L, or anything in between. So then we need to ask the question of what states can this atom be excited into? And as before, each starting state will have a different product state. So let's start again with the simplest case, this singlet p. So in this case, my p electron will be the one to be excited, and we can ignore any effects of this s orbital. And if I make that assumption, well, this p orbital can either be excited into an s or into a d, which will give us a corresponding L of 0 or 2. And because it is a singlet state, J must equal L. So if it's in the S state, I have a J of 0. And if it's in the D state, I have a J of 2. So in this case, that's a little fairly straightforward. It is worth noting, if the S electron were the one to be excited, it would indeed be possible to have a p state where the electron enters a p orbital that is pointing in a different direction as my initial p orbital. If you need to, take some time to draw that one out to help make sense of it. So that brings us to the next state. I have my triplet p with, again, this low energy J equals 0 case. So if this guy were to be excited, again, my p orbital can either enter an s or a d orbital, at which point I end up with a s or d state. Now, at this point, we note that if I have a J value of 0, the J cannot increase, it can't stay the same, so it must increase. So my only possibilities are a triplet S with a value of 1, which again makes sense because J has to equal S if L equals 0. And similarly, if I have a D state, we are now limited to the fact that my L of 2 and my S of 1 have to be coupled together because J can't change more than 1. So I end up with only 2 possible excited states. So we can apply the same logic to our 3p1 state. And again, at this point, despite the fact that selections rules say that J can increase by 1, if I look at the S state, Russell-Saunders say that this is, again, the only possibility. There is no such thing as a 3s2 state. But that brings us to the D states, which have no such limitation. So a 3D1 or 3D2 is possible. And we can extend this process to the triplet P with a J of 2, yielding one of 4 possibilities. So again, when working with electron excitations, it's worth noting that you can't rely just on what's allowed and forbidden according to selection rules. You have to keep in mind, in the back of your head at the very least, what excitations are physically possible, and don't forget to include Russell-Saunders. So this is a good process that brings a lot of what we've learned in electron excitations all together. So with that, this brings us to the end of atomic systems. Next time, we're going to continue looking at molecular cases. Time to get into some real molecular chemistry. Take care, stay healthy.